So at the end of the last lecture, we were studying a particular scenario, a pretty new one. So we had non-identical items. We had totally general valuations. Okay, so not submodular, nothing like that. But the twist in scenario 8 was that we had a lower bound on the supply of every item. Okay, usually we were just thinking of one copy of every item. In scenario 8, we have k copies, and the problem gets easier the bigger k is, the bigger the supply is. So we assume each bidder only wants one copy of a given item, but other than that, it's totally arbitrary. Okay, so there's m sort of types of items, k copies of each, km items overall, and valuations are defined only on subsets of u. Okay, and we just assume we only give one copy to a given bidder. Okay, but actually, we didn't even need that these were monotone last week, if you go back and look at the proofs. So these are totally general VIs. Okay, and for the purposes of talking about polynomial time, we're thinking of these as black boxes. All we do is we interact with them, and they support value queries and demand queries. It's not important right now, but the reason we needed demand queries was to solve an LP relaxation. That was the separation oracle in the dual that we needed to solve the LP. And so what we did last week is we said, well, let's put incentives aside and just focus on the algorithmic problem of welfare maximization. We postponed incentives until today. And for just the underlying welfare maximization problem, we showed that it can be solved in polynomial time almost optimally. Okay, so we had a really nice, strong, positive result. So like I said, the problem gets easier the bigger k is, so we need k to be logarithmic. So if you have log m over epsilon squared copies of every item, we gave a polynomial time algorithm that gets within a 1 minus epsilon factor of welfare maximizing allocation. And actually, let me say the theorem, and here's what we actually proved, because this is sort of a stronger statement than what I put on the board last time, but the proof actually showed this. The algorithm takes as input, it takes some feasible linear programming solution. So this was for that LP with the decision variables corresponding to bidders I and bundles S. And so it takes as input an LP solution, and then it did this randomized rounding. Okay, so it scaled down the solution slightly, multiplied all the y's by 1 minus epsilon. And then for each bidder, it gave it a bundle at random. Okay, and we did this independently for each bidder I. We had these YIS's, and that we just interpreted those as the probabilities of getting a given bundle S. And what we proved is that the expected welfare of the solution was almost as good as the LP solution, almost as good as what we started with, and there was a decent chance of being feasible. Okay, so as a result, if you just keep doing independent trials of this randomized rounding algorithm, you simultaneously get an allocation which is feasible, meaning every good is allocated at most k times, and also the welfare of that allocation is almost as good as that of the LP solution that you started with. Okay? So the particular y's that we were working with last week was the optimal solution of the linear program. That's the obvious one to use. But more generally, we didn't really use that fact. We just said, okay, give me a feasible LP solution, feed it into this randomized rounding, and this is what you get as output. Feasible plus almost as good as the fractional solution. Okay? So that's what we proved. This can also be, so I gave you a randomized variant. We're sort of thinking of just doing independent trials until it succeeds. It can be de-randomized. I'm not going to talk about it in class though. Okay, but it's sort of non-trivial but standard techniques from 25 years ago. Okay, so this can be made deterministic as well. So that's specifically kind of where we left off last week. Now, as far as the big picture, just so you don't lose the forest for the trees, what are we doing? So this is the sort of second and final week of part 2, where we're looking at sort of NP-hard versions of welfare maximization. I didn't say it, but this is also NP-hard. We can get close to optimal, but you can't get optimal. And we're still looking for this very strong dominant strategy incentive compatibility guarantee. Okay, so that's what we're doing now. And this is hard. This is one of the most challenging goals we're going to see all quarter. And the reason being is as soon as you pass to approximation algorithms, generally the VCG mechanism no longer works. And even more generally, we just kind of have a very sort of thin toolbox for designing multi-parameter DSIC mechanisms. And so the approach we're sort of doing is we're doing this bottom-up approach where we're just sort of grasping for whatever DSIC mechanisms we can find. We started with just the VCG mechanism. That's sort of all we had. So we said, okay, what could we do? Well, then the first baby step was maximal in range. So we said, well, I guess if we wanted, we could throw out a bunch of the outcomes up front and then run VCG on what's left. It's clearly DSIC. I'll give you one application of that for multi-unit auctions with non-downward sloping valuations. We had a 2 approximation. And so right now we're in the middle of the second baby step. Just like, okay, just these maximal in range mechanisms, they have some applications, but they're pretty limited. So the second baby step, which we introduced last week and we'll actually use in both of the lectures today, is the extension to maximal-in-distributional range. Okay. So a maximal-in-distributional range, or MIDR, allocation rule. So this is going to be a randomized allocation rule. And instead of pre-committing to a set of outcomes, it pre-commits to a set of distributions over outcomes. Okay, so script D is the set of distributions. Okay, whenever I talk about outcomes, I'm talking about them abstractly, but for our purposes, we're always thinking about allocations. So just a way of assigning the items to all of the bidders. Okay. So as far as right, so maximal in range, that corresponds to the case where all the distributions are just point masses. So this is certainly at least as general. What might these be? What is this distribution? It could just be an explicit list. Output this allocation with 1% probability, this other one with 3% probability, et cetera, et cetera, et cetera. Or maybe it's defined implicitly. Like for each item, assign it randomly to a bidder according to some distribution. Those are the kind of distributions we want to have in mind in script D. Now, this is in the spirit of VCG, so there should be some flavor of exact optimization. So by definition, once you've settled on this set of distributions, the allocation rule is uniquely defined. Okay, so basically, given that we're going to sample an outcome from one of these distributions, we insist on picking the distribution which is best for the bidders, okay, just in the spirit of VCG. So what's best for the bidders, it just means maximizes their expected welfare, given that we're going to sample from the distribution. Okay. So it outputs, so I'm going to use sometimes little omega as shorthand for an allocation. But just think of, always little omega is some S1, S2 up to Sn, the items assigned to all of the bidders. Okay? So it outputs some outcome or some allocation drawn at random from the best distribution, D star, again, meaning that among all of the candidates, so all of the distributions in script D, D star should give the bidders the maximum possible welfare, where here VI denotes the reported valuations of the bidders. Okay? So again, sort of given that we've pre-committed to this distribution set script D, and given that we're going to sample an outcome from one of these distributions, we should pick the best one. Okay? And then what I asked you to do as an exercise for exercise set 4 is to verify that there's a natural analog of VCG payments, which when you couple them with this allocation rule gives you a DSIC mechanism. So this is a randomized allocation rule, so here we're defining DSIC to be bidders maximize their expected utility, where the expectation is over the coin flips in the allocation rule by revealing their true valuation. So we're thinking about risk neutral bidders. Okay? All right, so that's kind of where we were. Now that sort of everyone's here, let me just sort of pause for the quick course announcements. So there are only 2 required problems in exercise set 4. Those are due today. I'm going to post an exercise set 5 soon. That's going to be completely optional. I'll just have 2 or 3 optional questions. So be on the lookout for that today or tomorrow. So the big news is that all the project deadlines are now sort of settled and all the project suggestions are up on the website. You should have an email with the link to that. So by Friday, so this is for those of you taking the course for a letter grade, by the way, only. So if you're taking the course for a letter grade, send me at least 2 topics you're interested in by Friday. And then over the weekend, I'll sort of write people back with confirmations of the project topics. There's 2 deliverables. One, just to sort of keep people on track, is I do want a 1 to 2 page outline. There's more detailed instructions on the website. So that's going to be due March 5th. That's a Wednesday, and that's 2 weeks before the final report is due. This is the Wednesday of finals week, March 19th. And just ballpark 12 to 15 pages. There's both more detailed instructions. There's also a sample report all posted on the website. Okay? And again, feel free to just get in touch with questions, either picking the projects or afterwards. Happy to help. Okay. All right, so any questions? Okay. Right, so we have on the one hand, all right, so basically we have these MIDR allocation rules. We've defined them, we haven't used them. There's this problem where we know how to solve it without incentives, and so no prizes for what comes next. We're going to use these allocation rules to get just as good an approximation for that problem with incentives. Okay, that's the plan for this lecture. And then the second lecture today, we'll go back to what kicked off this whole NP hardness discussion, submodular valuations, and we'll give a second application of MIDR allocation rules to get a constant factor DSIC mechanism for a subclass of submodular valuations. Okay, so that's the plan for today. Full disclosure, this is probably going to be the most sort of technically intense lecture of the quarter, would be my guess. So I'm not going to say it's easy after this, but if you can survive today, I think it'll all be downhill from here. And also the lecture right now, this first lecture will be the longer one. The second lecture will be the shorter one for today, probably. Okay? So that's just what you can expect. All right, so let me just remind you, why are we doing this? So why, why did we define these MIDR allocation rules? Well, one thing is we're just trying to brainstorm about what else might possibly be DSIC. But I mean, can we even think of why this might be useful? And so the hope, which you shouldn't necessarily believe until I show you the actual examples. But the hope would be, in the same spirit that, if you have a discrete problem which is hard, like an integer program, and you relax it to a linear program, you allow more solutions, fractional solutions, that can somehow create tractability when it wasn't there before. So this is sort of the daydream. Now, a couple warnings. So first of all, this analogy is not perfect. So when you relax an integer program to a linear program, you keep all the integer solutions and you get a bunch more stuff. You get stuff which is usually strictly better than the integer solutions. We've seen that already. And that's not really what's happening when you pass to an MIDR allocation rule, if you think about it. Right? So you have these integer solutions, these allocations, and we're passing to things which by definition are distributions over allocations. Okay? So you're not going to have anything strictly better than an allocation. You're only looking at distributions of allocations. Okay? So in particular, if you think of an MIDR allocation rule, and it happens to be the case that in this set script D, that includes all the point masses, all the integer solutions, well, you're not going to do better than an integer solution with a distribution. Okay, so if you have all the integer solutions in D, all the point masses, you haven't made your life any easier. Things have not gotten more tractable. You're optimizing over just as hard a set as before. So that's a little different. So somehow these set script D have to be chosen, and a fair amount of work has to go into figuring out what the right script D is. We'll see that today. And then the second comment is, we will see a couple of nice applications of MIDR allocation rules, but they're really still, pretty limited in use. And so, it'll never be the case that you design some randomized algorithm and you get lucky and it happens to be MIDR. Okay, that just basically never happens. You have to basically channel all your design creativity into ensuring the MIDR property. Now, again, we'll see a couple of positive examples, but I mean, it's really a pretty limited kind of playground that we're working in to design these rules. Okay, that was true for maximal in range rules also. You never accidentally get a maximal in range approximation algorithm. You have to sort of begin the exercise trying to get that property. Okay. Okay. So. Today, so in the first lecture, I want to focus on a special kind of MIDR rule. Okay? And I'm going to call these scaling algorithms, which is a very restricted form of randomized rounding. Randomized rounding, we've already seen an example of last week in the just approximation algorithm. Okay? So let me explain how I want you to think about randomized rounding of linear programs for today. And we're going to be, this will be sort of our perspective in both lectures today. So we think about algorithms, approximation algorithms, that are the composition of two steps. Okay? So in the first step, you solve a linear program, and in the second step, you round it to an integer solution. Okay, and so the LP you should have in mind is just the one we were working with over the last couple of weeks, with the YISs as decision variables. So the LP, you can think of as that as taking these valuations as inputs, as specified by a black box supporting demand queries or whatever. So the first part of the algorithm takes as input the the valuations, and then it solves some LP optimally, and it spits out an optimal LP solution, Y star IS. Okay? So this was exactly the first step in our algorithm last week. Then we have what I'm going to call an oblivious randomized rounding algorithm, R. So the responsibility of the first box is just to produce an LP solution, and the responsibility of the second box is to compile this LP solution, which in general is not a distribution over allocations, into a distribution over allocations. Okay, so that is just going to randomly pick some allocation. So over here we're going to get a distribution, and I'm going to use the notation R of y star as the distribution over allocations implicit in this rounding algorithm. Okay? All right, so a couple comments. So what do I mean by oblivious? So what I mean by oblivious here is that once you give the rounding algorithm, this LP solution, the y's, it doesn't look at the original input, the valuations that generated these y's. Okay? So basically, the rounding algorithm depends only on the y's, not on the v's. That's what I mean by oblivious. In principle, you can imagine randomized rounding algorithms which not only use the y's but go back and look at the v's again to do clever rounding. Okay? So today it's going to be oblivious, and it doesn't do that. And if you think about the randomized rounding last week, it was oblivious in this sense. It just looked at the y's, scaled them down, and then flipped coins according to the y's. Okay? So that's what I mean by oblivious. And again, let me just remind you that this LP solution in general is strictly better, right? So in an LP relaxation, including the one we're looking at here, the y star is strictly better than any integer allocation. Okay, so therefore it's not by itself a distribution of allocations. That's what happens in this final step. Okay? All right, good. So the question now is, what is the relationship between a randomized rounding algorithm and MIDR allocation rules? Are they the same, or can they ever be the same? Okay? So at a high level, we might hope that randomized rounding is a good candidate class of algorithms to generate MIDR rules. Remember what MIDR says. It basically says you should always be picking the best distribution. Okay, so you're optimizing over distributions. Randomized rounding has this sort of nice, there's some syntactic connections, in that you are explicitly doing an optimization over fractional solutions, and you're outputting distributions which have some connection to what you're optimizing over. Okay, so MIDR says optimize over distributions. This picture, well, you optimize over the y's, and then the y's sort of generate these distributions. So that sounds like it's on the right track. The reason why randomized rounding algorithms like this might not yield MIDR rules is because what we really want to be optimizing over, if you look at the definition of MIDR, we want to be optimizing over this output here. Okay, we always want to be outputting the best distribution of our allocations for the given v's. But in this picture, the optimization's happening over here. The optimization's happening over the LP solutions. The optimization is not explicitly happening over the distributions. Okay? So the worry is that there's some disconnect between those two introduced by the rounding algorithm R. So scaling algorithms are going to be the specific kind of randomized rounding algorithms where optimization over the fractional solutions is exactly the same as optimizing over the distributions. Okay, so it's exactly the class of capital R's that give us the MIDR property in this schematic picture. Okay? All right, so what is it? Simple enough to state. So an oblivious randomized rounding algorithm is an alpha scaling algorithm. So here alpha is a number between 0 and 1. If whatever you feed it, so whatever feasible LP solution you give it y, if you look at any bidder and you look at any bundle, the probability that bidder I gets this bundle, okay, in the output of this rounding algorithm is exactly what the LP suggests, y star is, multiplied by alpha. Okay, so think of alpha as like 0.9. So the probability, and again, so what's the coin flips here? The coin flips is over what the randomized algorithm does. So remember, y is an LP solution that gets fed to this rounding algorithm. It flips some coins, it outputs an allocation. And so an alpha, so the probability that I gets S is exactly the suggested probability, or we're going to interpret this as the suggested probability of that event by the LP solution times alpha. Okay? And again, let me remind you, we would not expect for some NP-hard problem like this, we would not expect to ever have a one scaling algorithm. Okay? Remember, these LP solutions in general, they're going to be strictly better than any integer allocation. Okay? So if we had a 1 here, that would say we're giving people exactly what the LP is giving them in expectation. Okay? So we'd be getting in expectation the full value of the LP, and we don't expect to get that. The LP is going to be strictly better than any integer allocation. So we want this to be scaled down, or we expect this has to be scaled down, but we're hoping alpha is as close to 1 as possible. Okay? Alpha will correspond to some approximation guarantee. Okay? All right, so is that definition clear? Okay, so the motivation I think will become more clear as we go along, but at a high level, the point of this definition is so that by optimizing over an LP, you wind up inadvertently optimizing over the distributions in your range. Okay, and we'll see that that happens. Okay, but everyone can parse this, okay? All right. So let me now show you why, if you have such an algorithm, you're good to go, and then we'll worry about, okay, do such algorithms exist? And if so, how do we get our hands on them? Okay, so claim, if we have an alpha scaling algorithm, then the induced allocation rule, X, is MIDR. And so what I mean by induced allocation rule, I mean the allocation rule where you solve the LP optimally, and then you apply the scaling algorithm, okay, to randomly generate an allocation. That's what I mean by the induced allocation rule. So the claim is scaling algorithms are a sufficient condition to turn for a randomized rounding algorithm to give you an MIDR rule, and therefore a DSIC mechanism. Okay? So the proof is easy because we define scaling algorithms to make it easy. All right, so MIDR just means of all the distributions over outcomes that we might ever see, varying over all valuations, for a given valuation, the algorithm picks the one that maximizes expected welfare. So what is the range, the distributional range of this allocation rule? Well, it's just, as you range, so conceptually, imagine just over the LP solver, imagine feeding this every possible input in the world, every possible valuation profile, okay? So you get back some set of, every possible output, every conceivable Y's that you ever get from this LP solver. And from each of those Y's you might get, imagine applying the randomized rounding and you get some corresponding allocation distribution over the allocations. Okay? So the range of X is simply the output distribution of the randomized rounding algorithm applied to any conceivable LP solution that might be fed. Okay? Now here's the key point. So here's what's special about scaling algorithms. So no matter what feasible LP solution Y you feed the rounding algorithm R, you get that the expected welfare of the allocation at the end of the day is exactly the same as the LP solution you started with multiplied by alpha. Okay? So the expectation here, let's look at the allocation. So again, omega drawn from R of Y, just think of this as like the output of the randomized rounding algorithm and its expected welfare. Okay, that's what we're saying. So this is just the welfare of omega, and again, omega is just the random output of the randomized rounding algorithm. And just by linearity of expectations, we can just do this as a sum over bidders. And now for a given bidder, let's just kind of brute force sum this. Let's just say, well, think of every bundle S that bidder I might get. It has some value for that bundle, and then it contributes to this expectation, the probability that I actually gets that bundle, where again, this is over the coin flips in the randomized rounding algorithm. And now by definition of an alpha scaling algorithm, this is equal to just the alpha times the welfare of the fractional solution given by the Y's. Okay? So the point is, you solve this LP, you get some fractional welfare, 1230 or whatever, which in general is strictly bigger than the welfare of any integer allocation. You feed it through this randomized rounding algorithm, and you just know exactly what's going to happen. The expected welfare is going to get scaled down. It's going to get scaled down by alpha. Doesn't matter what Y was. Okay? It's always scaled down by exactly the same amount, like always 0.9. Okay? So why is that good? Well, so again, remember, what do we need to have the incentive properties? We need to be optimizing over the distribution of our outcomes, right? That's the definition. Okay, we need to pick the best distribution. What are we actually doing in our algorithm? Well, we're not explicitly optimizing over distributions, we're optimizing over LP solutions. But this basically says that the two optimization problems are exactly the same if you're going to round using capital R, this one algorithm. Okay, so optimizing, picking the best distribution for the expected welfare, is exactly the same as picking the best fractional solution y for the LP solution. Because there's just this linear relationship between the two quantities. Okay? So upshot, R of y is optimal for a given input, where here by optimal I mean over all distributions in the range of the rule. If and only if y is optimal for the same valuation profile, where here by optimal I mean over LP solutions. Okay? So again, the expected welfare always drops by exactly the same factor alpha. So by explicitly optimizing over the LP solutions y, you wind up implicitly optimizing over the distributions over allocations. Okay? And that's the definition of MIDR. So that's the claim. Okay? So since y star is chosen optimally, that means we're choosing the optimal corresponding distribution. So the allocation rule is maximal in distributional range. Okay? So maybe just to sort of talk through this a little bit more. So like what would go wrong? So like imagine instead of this definition, instead of alpha scaling, I only promised you that for every y, for every I, for every s, the probability is at least alpha times what the LP suggests. Okay, so maybe alpha is like 0.9. So I say, well, you know, I don't know exactly what the probability is going to be, but I promise you it'll be at least 90% of what the LP wants it to be. Okay? Because often the kinds of guarantees we prove in the analysis of, you know, approximations, right? It's 0.9 or better. So this claim is not going to be true, right? Assuming only that this is at least 0.9 always. Why? Well, maybe you had these two LP solutions, right? Y1 and Y2. So you have a given input. You have these valuation profile. And there's these two competing LP solutions, Y1 and Y2. Okay? And with respect to the LP objective, they're almost the same. Okay? Like Y1 is 1% better than Y2 for this valuation profile. Okay? And maybe it happens that when you then apply the rounding algorithm, though, very different things happen. Okay? So with Y1, when you round it, you actually only get 80% of it on average in the allocation. Whereas Y2, for some reason, just is, you know, better friends with the rounding algorithm, and you get 90% of Y2 when you round it. Okay? So you started with LP solutions where Y1 was better than Y2, but then after the rounding algorithm, they flipped. Okay? It turns out for the bidders, they actually would rather you started with Y2 than started with Y1. Okay? They'd have preferred you started with a suboptimal LP solution because it does better in surviving the rounding algorithm. Okay? So that's why it's really important that we have equality here for this claim to work, for that MIDR to work. Okay? So any questions about that? So again, at a high level, you know, you can kind of reverse engineer everything we've said so far. Right? You can come up with this idea of MIDR just by asking, is there a randomized analog of the VCG mechanism? The answer is yes, and it's MIDR. Okay, that's just what you'd come up with by answering that question. Then you sort of recognize that this is sort of a pretty hard property to ensure. And so now you want to ask, okay, well, what kind of crazy conditions can I envision on an algorithm where I'm guaranteed to get this property? And randomized rounding looks like a good place to start because there's optimization and there's distributions. And then you realize you need this very tight control over how the LP solution is rounded to have this correspondence between optimizing over the LP and optimizing over distributions. And the control that you need is basically this definition of a scaling algorithm. Okay? So that's where things stand right now. Any questions? Okay. So what you should now appreciate is that if we can come up with these alpha scaling algorithms with alpha close to 1, we're happy. Okay? We're going to get good approximations. It's going to be MIDR, so it's going to be DSIC. So now, are there any? Well, actually, let's start with this first question, sort of an interesting question. Let's actually think about the rounding algorithm, R, which we used to prove this theorem last week. So let me remind you how that went. It follows this exact same blueprint. We first solved the LP, we got our Y star. We scaled Y star by 1 minus epsilon. That sounds kind of like a scaling algorithm, right? We scaled it down so we could be feasible with high probability. So then we scale it by 1 minus epsilon, and then we do this independent randomized rounding. Okay? And then we do independent trials until we get sufficiently good welfare, close to the expectation, and we're also feasible. And then when we get one, we stop. That was the randomized version. So is that a scaling algorithm or not? It's kind of a subtle question. Any guesses?
No.
No, why?
Because there's a small probability that you're going to have to do something strange at the end, and that probability, the size of the probability is going to depend on why.
Good. So that's, I underspecified the algorithm, and for one of the natural things I might have meant, that's exactly the right answer. So how about the following version of the algorithm, which is I just keep doing independent randomized trials, and I wait until I get something, and I just wait. I never do anything weird. I just wait until I get one that has good welfare and that's feasible. And that's going to happen eventually with probability 1. So the version of the algorithm where I do it a polynomial many of times, and if none of them work, then I do something else, you're exactly right. Yeah. So yeah, go ahead.
So what happens is maybe a certain allocating S to I makes it more likely that they'll succeed, which means that you get higher than alpha times y star for some of them, and then lower for other ones.
Good. Yep, exactly. So the short answer is that with the version I just said, where you wait until you get something which is both feasible and has high welfare, it's not the case that the distribution is exactly 1 minus alpha times the previous one, because you've conditioned on stopping. Okay? So when you flip the coins and you don't condition on feasibility, then indeed the probability that you get a certain bundle is exactly 1 minus alpha times what the LP said. That's by definition of your algorithm. But if then the final output is stopping, then there's this conditioning on the stopping rule. And so concretely is exactly what you said. It may be the case that, if I told you that the algorithm stopped here, I told you it was feasible and it had good welfare, maybe you could make inferences like, oh, well then for sure, this coin flip came up tails. Because if this person got this bundle, that would totally screw everything up. Exactly. You have a comment on it? Or?
Well, if you just terminated, did one flip and then terminated, then it would be. I don't know how good the alpha would be there.
Well, so the problem is it wouldn't be feasible. So that's exactly right. So if you
but if it wasn't feasible, then you just say, well, no one gets anything.
Ah, I see. Excellent point. Yeah, you could do that as well. That's that would give you a worse alpha. Yeah, exactly. Right. So you do it once. Now, is that true? No, I think you still have a conditioning problem, right?
Oh, right. No, you
same conditioning problem.
Yeah.
So if you drop the feasibility constraints and you just said this is the allocation, then you sort of have it by fiat. Yeah. But this, so that's the problem. So I wish it was a scaling algorithm, because then we could skip 30 minutes of lecture, but it's not, okay? So the incentives are actually wrong, all right? If you try to plug in the algorithm from last week into this schema, if you try to do VCG payments, it's not gonna work. It's not gonna be DSIC, it's not gonna in general be approximately DSIC. So it is important that that thing exists. There's a reason that we went through it. So instead, we're going to do something kind of remarkable. We're going to show that just by virtue of their existing, a 1 minus epsilon approximate randomized rounding algorithm, which is not scaling, by virtue of that existing, we'll show that implies that there must exist an equally good randomized rounding algorithm, which is a scaling algorithm. Okay? And we'll explicitly use the existence of this one we built last week in that proof. Okay? You can think of what we're about to do as somehow taking that old approximation algorithm and smoothing its errors equally across all inputs. That's sort of morally what we're going to do. Okay? Okay. So here's what we're going to do for this. What we're going to prove this first lecture. Okay, so this is a result by Levy and Swamy from mid-last decade. So in the current scenario that we're talking about, under the same lower bound on the supply, there does exist a polytime 1 minus epsilon scaling algorithm. And because of everything else we've said, that gives us a 1 minus epsilon approximate polytime MIDR and hence DSIC mechanism. Okay? Which is really, I mean, just as a result, this is pretty cool, right? Especially if you think that we haven't imposed anything on the valuations, right? This is actually a really strong positive result. So first of all, we're doing just as well as without the incentive constraints, okay? So without incentive constraints, 1 minus epsilon is the best you can do. We're getting 1 minus epsilon with DSIC, the best incentive constraints. And then also, of course, the approximation ratio is excellent. Okay, it's basically going to 1 once the supply is logarithmic, getting at least logarithmic. Okay, so we have to work pretty hard, but as a guarantee, it's pretty compelling, I think. Okay, so what's the plan? So let me tell you at a high level how this is going to work. All right, so here's how we construct the scaling algorithm. Okay? So we're given as input the optimal solution to the LP. I'm going to call it the original LP for reasons to become clear. This is the input to the scaling algorithm, to capital R. Now here's what we're going to do. We're actually going to solve a second linear program whose feasible solutions are encodings of scaling algorithms. Okay? So we're going to have to show this linear program is feasible. That is, there exists a scaling algorithm, and I'm also going to have to show you that we can compute one in polynomial time, and I'm also going to have to show you that we can sample from that scaling algorithm in polynomial time. So we'll get all of those things sort of in one fell swoop, but those are all important properties. So we're going to solve a second linear program to compute a probability distribution, capital lambda. And the probability distribution is going to be explicitly specified. Okay, so it's just going to be a list. It's going to be here's allocation 1, spit it out with 1% probability. Here's allocation 2, spit that out with 3% probability, and so on. Okay, so probability distribution, explicit. Again, remember, omegas represent outcomes, as in allocations. Such that, okay, so L, the support of this distribution is going to be polynomial size. And this is going to be a scaling algorithm, meaning that the probability, if you sample from capital lambda, that I gets S is going to be equal to, so our alpha is going to be 1 minus epsilon times y star is for all is. And given that it's just an explicit probability distribution that has small size, then you can just sample from it efficiently just by brute force. Okay? So explicitly, so that's not hard. Given, if we can implement 2, then sampling from it is easy. Okay? So the content here obviously is step 2, right? So how do I do that? Right? But this is the plan. Okay? So you agree that if we can do this, then we're done. We have our 1 minus epsilon scaling algorithm. Okay, so details for step 2. So first things first, let me actually explain the second linear program to you. Okay? In some ways, it's the obvious one. I mean, it's just, we're literally just going to, like, in effect, by brute force, look. So, okay, Y linear program. So remember, we're given our target probabilities, right? So we're given as input, these fractions, which is sort of our target probability of giving S to I. So these are just numbers, remember, these Y stars. So these are not decision variables. Y stars are given. So these are just linear constraints. Okay, this idea that we should, be scaling down probabilities by exactly alpha. So that's why, a linear program seems like something you might want to use. Okay. All right, so we're going to have to, all right, so a quick technical point. So Y star, this LP solution, remember what these decision variables are. Okay, there's one for every bundle I, and there's one, sorry, for every bidder I, and one for every bundle S. That's a lot of decision variables, right? There's n choices for I, and there's 2 to the m choices for S. Okay, so there's zillions of potential decision variables. On the other hand, remember, this is what we did a couple weeks ago. We computed Y star in polynomial time, right? That was this thing where we sort of went to the dual, used the ellipsoid method, and then the separation oracle was the demand oracle, et cetera, et cetera, et cetera. Okay, so Y star is the explicit output of some polynomial time linear programming computation. Okay, so there was not time to write down n times 2 to the m decision variables when we solve for Y star. Okay, there's only a polynomial number of non-zero Y stars because it was done by a polynomial time computation. Okay? So let I be the non-zeros, the indices for the non-zeros in Y star. Okay? So poly size. So I is poly in n, m, and the number of bits in the original linear program. Since explicit output of a polytime computation. Okay. So why do I mention that? Well, so looking ahead, I mean, like as I alluded to, these are going to be constraints in some linear program, and this means we can only worry about the non-zeros. Okay, it means there's going to be a polynomial number of constraints. That's why this is an important observation. Okay. So notation. So let omega be, as usual, all possible allocations. So this is what remember, we're searching for a distribution over allocations. Okay, so somehow decision variables are just going to correspond to the probability mass on a given allocation. And then, because we're interested in the probability that a bidder gets a bundle, we should keep track of, for a given I and S, the allocations where I gets a particular bundle S. Okay? And so now what is this second LP? So the second LP will literally, you just have a decision variable, lambda omega. So this just represents the probability mass we're going to put on the allocation omega. Okay, so remember, we're solving for basically like a randomized rounding algorithm. We're solving for a distribution of allocations. This decision variable just is going to be something like 1%. Output this allocation with 1% probability. Should be a distribution, so let's make sure that they sum to 1. And then, of course, there's a whole raison d'etre for this thing, which is getting the scaling constraints. Okay? So I really should write for all IS, right? We really want to preserve the probability of every single bidder bundle pair. But again, I don't want exponentially many constraints here, so I'm just going to focus on the non-zero Y stars. Okay, so the Y stars in I. So, okay, so what should be, so the right-hand side here, we know what this is supposed to be. The probability mass of the allocations where I gets S is just supposed to be, by the definition of a scaling algorithm, the target Y star IS scaled by 1 minus epsilon. And then the left-hand side here is just going to be all allocations where I gets S. Okay? So that's the LP. LP2. Any complaints? There's potentially a complaint about this LP, actually, given what I said it was supposed to do. So I'm trying to encode scaling algorithms that meet this condition. And I didn't quite do that. I wrote down a smaller LP, right? So these are the constraints saying I'm supposed to respect the target probabilities, the Y stars, and I only wrote them down when the right-hand side was non-zero. Okay, I just didn't write down the ones that were 0. And if you think about it, it's not obvious that if you solve this smaller linear program, you're going to get something that respects those zeros. Okay, so it might be the case that there's some missing constraint where IS is not in I. meaning y star is 0, is the right-hand side 0, and maybe the probability mass on the left-hand side adds up to 2% or something. But there's actually, if you think about it, an easy sort of post-processing hack to fix that. So the claim is that if I think of any feasible solution to this linear program, then it induces a scaling algorithm in this sense. So by fiat, any solution to this linear program respects all the non-zeros, so that's no problem. So what I can do is I can just, take the feasible solution, sample from it. If I ever see a forbidden pair in the output, okay, so I pick an allocation from this randomized solution, and if it's ever the case that I get to bundle S where IS is not an I say, oh, just kidding, and I take it away from them. Okay, so I just sort of zero out forbidden bitter bundle pairs after the fact. I just force them to be 0. Okay, so that's not the hard part, right? So if you think about it, like enforcing that this distribution has a 0 probability of giving some bitter, some bundle, that's really easy to enforce after the fact. So that's why I can get away omitting it from the LP. Okay, so the hard part is for the non-zeros getting it exactly right, and that's done explicitly in the LP. Okay. Okay, so summarizing note. Every feasible solution induces, I'll say, induces a 1 minus epsilon scaling algorithm. Okay? Just by canceling forbidden bitter bundle pairs after the fact. Okay. So does everyone agree that if this thing is actually feasible, remember, a priori, this could be empty. We have no idea, right? I can write this down. Doesn't mean it's like useful, right? But if this is non-empty, and I show you how to compute a feasible solution in polynomial time, and moreover, the feasible solution has small support, then that's an implementation of step 2 here. Agreed? So that's what I owe you at this point, okay? I owe you non-emptiness, tractability of the solution, and small support of the solution that gets computed. Any questions modulo that? All right.
And I just want to check, there's an exponential number of lambda omegas, right?
Excellent, yeah. Sorry, I should have mentioned that immediately. So, yeah, there's a lot of lambdas, okay? So there's a lot of decision variables in this linear program. Okay, so remember, omega is an allocation, a way of assigning items to bidders. And there's a zillion ways you can do that, right? Each of the m items can go to one of n bidders, okay? So that's m to the n, right? N to the m allocations, okay? So, which is another reason why I really wanted to make sure that we had, to have any kind of prayer, right? So if both the number of variables and the number of constraints are polynomial, as a linear program, we're good to go, right? Use any polynomial time method, it's fine. If both are exponential, forget it. There's nothing you can do, basically. If one of them is polynomial, you at least have a hope through the ellipsoid algorithm, if you have a separation oracle, okay? So at this point, it's not at all obvious we can solve it, but it's not obviously hopeless. And this is the comment about why it was so nice to have only a polynomial number of non-zeros in y star, and dropping all but a polynomial number of constraints. So at least the number of constraints is small, but the number of variables is huge, absolutely.
I guess I just have a question about knowing that there's a polynomial number of non-zero y stars. Because in the Ellipsoid method, we were solving the dual, right?
Yeah.
And so you would have to reconstruct the...
You're absolutely right. I'm glossing over this on purpose in lecture. So if you look at so the notes for lecture 8, which are not posted yet, but they're about to be posted, include full details on that. Let me just say a little bit about how it works. So basically, so what I wrote here, this is kind of more like morally this should be true. It's not actually true that I've proven this to you in class at any point. But so, well, actually, we'll have to deal with this later this lecture. And so I'll point out where we're dealing with it again. And it also explains why this is true. Okay? Yeah.
I mean, one quick way of proving it is just to realize that the dual of the dual comes back to the primal, right? So if you assume your algorithm is polynomial, then you can have a polynomial number of constraints that are actually active at your optimal solution. And each one of those constraints is going to correspond to a non-zero dual variable. or is the only possible?
A non-zero variable back in the primal.
Yeah, it's primal.
Right. That's exactly right. So that's sort of the missing trick. I'll say this again when it's relevant in this lecture. But basically the idea is, I'll point out in this, we'll see it explicitly in this lecture. So I'll point it out where that is. Yep. But Ollie's exactly right. Okay. So, right. So we have this linear program, exponential number of variables, polynomial number of constraints. Maybe we can solve it by ellipsoid. That's going to be the plan. We will. That'll be the plan. And now again, just like with the welfare maximization and relaxation, again, sort of the dimensions are the ones that are backward from what we can handle, right? So the ellipsoid algorithm, you'll recall, it needs the dimension, the number of variables, to be small. It can handle a large number of constraints. So in this linear program, it's backward. So if there's going to be something we can solve, it's going to be the dual. So let's understand the dual of this problem, okay? All right, so thought experiment. So we're hoping this is feasible, right? Sort of our whole approach of having scaling algorithms work hinges on this thing being feasible. So let's play devil's advocate for a moment. Suppose I wanted to convince you that this was not feasible, okay? A proof of infeasibility. How would I do that? What would be sort of a convincing short proof of infeasibility? And then, as usual, these proofs of infeasibility will be just the dual linear system. Okay, well, suppose I could come up with the following, all right? So suppose I could somehow dream up what I'm going to call pseudo-valuations. ZIS. And I'm calling them pseudo-valuations because these are not, I'm not going to assume that these are non-negative. Okay, they can be negative. And I'm not going to assume they're monotone. These can be literally any real numbers satisfying the constraints I'm about to write down. So suppose I can find these pseudo-valuations, these ZISs, so that the following are true. So first of all, other than these indices in capital I, these are 0. So basically there's a ZIS. I mean, these things are going to correspond to multipliers on these constraints. These are going to correspond to dual variables. So in particular, they're going to correspond to these constraints. So outside of the bidder bundle pairs in capital I, implicitly we'll think of them as 0. Okay, so but now here's the interesting part. Suppose it's the case that the max, the largest possible pseudo-welfare of an allocation, where by pseudo-welfare I just mean you sum up the ZISIs. Okay, so again, this is a thought experiment. So imagine for every imaginable allocation in the world, if I treat the z's as valuations, even though they're just made up numbers, if I think of them as valuations and I look at the corresponding welfare, and I call this largest possible pseudo-welfare you ever see z star, suppose this is strictly less than 1 minus epsilon times the pseudo-welfare of the solution y star that we started with, that are supplying our targets, okay? So sum over I equal 1 to n, sum over subsets, ZIS times y star is, okay? So the claim is if I can find pseudo-valuations meeting these properties, then certainly there's no hope in there being a feasible solution of LP2. Okay? So this is what I'm going to prove to you next. If pseudo-valuations satisfying these exist, then LP2 is infeasible. Okay? And this is just an analog of weak duality. All right, so why is that true? So then LP2 is infeasible. So then we'd be doomed, okay, if this thing exists. So we're hoping this doesn't exist. All right, so reason, well, so just think of these ZISs as multipliers. Okay, so imagine We multiply the constraint here by ZIS, and we multiply this constraint actually by minus Z star. And then we add up the results. Okay? So with multipliers minus Z star for the normalization constraint, and then the ZIS's. So what would then be true about the right-hand side? Okay, so again, suppose I multiply this by minus Z star, and I multiply each of these by ZIS, and then I add up the results. Right, so on the right-hand side, I'm going to get a scalar. I'm going to get one number, right? There's going to be a contribution of minus Z star here. And then each of these constraints contributes 1 minus epsilon y star is times ZIS. Okay? Well, by assumption, this 1 minus epsilon summed over all these constraints, the y stars times the ZIS's, this is strictly bigger than Z star. Okay? So these constraints contribute the right-hand side here. This constraint contributes minus of that. So you add them up, you get something strictly positive. Okay? So right-hand side is strictly positive if I multiply the constraints with these particular coefficients. On the left-hand side, so what's the coefficient of each lambda omega on the left-hand side? So fix omega, omega is just an allocation. Okay, S1, S2 up to Sn. Definitely shows up exactly once in this constraint. So that's contributing a minus Z star, okay, to the coefficient of lambda sub W in the sum. Here, so for a given allocation omega, it participates in exactly the constraints corresponding to Bitter bundle pairs IS, where a Bitter I gets that bundle S in this allocation omega. So summing over all of these with the multiplier ZIS's, the contributions to the coefficient of lambda omega is exactly the pseudo-welfare of omega. Okay, it's exactly the sum over the bundles SI going to I, the corresponding ZI of S value. Okay. So is non-positive. So again, this is contributing minus Z star. This is contributing the pseudo-welfare of omega. And by assumption, the pseudo-welfare of every single allocation, in particular this one, omega, is at most Z star. Okay? So minus Z star cancels out all the pseudo-welfare. So given these two properties, now we see why LP2 couldn't possibly be feasible. Right? All the lambdas are non-negative. So if you have a bunch of things that are non-negative, all with non-positive coefficients, that's going to give you a non-positive number. And yet, supposedly, it's supposed to be a positive number. Okay, so there are no lambdas that could possibly satisfy this summed up set of inequalities. All right? So again, the point is, this is just kind of a linear proof of infeasibility of LP2. Okay, I show you a particular, so you need to satisfy all the coefficients. I've shown you this particular linear combination of the coefficients, which there's no way you can satisfy. I've made it obvious you can't satisfy them by making all the coefficients on the left-hand side non-positive and making the right-hand side strictly positive. Right? So no way. Okay, good. So if there are pseudo-valuations with these properties, then certainly LP2 is infeasible. And the dual, then just by definition, is the set of all proofs of this form, okay, the dual linear system. So the decision variables are just the Z star, the multipliers, and the ZIS. These are unrestricted. And then these are the constraints. Okay, so it should be the case that all integer allocations have pseudo-welfare at most Z star. So Zi of Si. So that's what that says. So this is, right, for all allocations, And I apologize, I'm going to switch back and forth between the notation for allocations omega or just S1 through Sn as convenient. But it's always the same thing. Little omegas are always S1 through Sns in this lecture. And then this should also be true. Right, so the pseudo-welfare at the fractional solution of y star should be bigger than z star. Okay? So what I've proven to you, again, the analog of weak duality, which is if D2 is feasible, if this dual linear system is feasible, then LP2 is infeasible. Okay? So they can't both be feasible. That's a weak duality. Strong duality, so which in this just sort of simple feasibility context is just Farkash's lemma, the theorem of the alternatives, says it's also impossible that both are infeasible. Okay? So I proved to you they can't both be feasible. I'm going to state without proof that they can't both be infeasible. Okay? It's not that hard to prove, but it's outside the scope of this course. Right? It's just strong duality, basically. So strong duality, they can't both be infeasible. So exactly one is feasible. All right? So in other words, what's easy is that if there's a proof of this form, you're dead meat. But if there's no proof of this form, you have to be feasible. Okay? So which is great, because what do we want? We're crossing our fingers that this has a feasible solution. These are the scaling algorithms. Don't forget that. Okay, this is what we're searching for. These are the scaling algorithms. So it says all we need to do, quote unquote, is prove the infeasibility of D2. And then we're good to go, at least with respect to existence. Then there's computational tractability as well. Okay. So again, just to recap, where are we? What I need to prove to you is that this has a feasible solution. You compute one in polynomial time, and it has polynomial size support. Okay? The way we're going to prove all three of those things in one fell swoop is to run the ellipsoid algorithm on this linear system, okay, on D2. So approach, run ellipsoid on D2. And the reason that's not crazy is, and the whole reason we're looking at the dual is this has a polynomial number of variables, right? So this has a variable. I should have written this. So this is for all, these correspond to constraints in the primal, which correspond to the non-zero variables in the original LP solution y star, of which is a polynomial number. Okay. There are, unfortunately, an exponential number of constraints in the dual, one for every possible allocation, S1 through Sn, but now we can at least hope that we have a separation oracle. Okay. So let's drill down on the separation oracle. So remember how this works. The separation oracle is given as input an allegedly feasible solution. So in this context, it's going to be candidate values of the ZISs for all allowed bidder bundle pairs IS and a Z star. And the responsibility of the separation oracle is either to say, yes, it's feasible, or if it's infeasible, to give a proof in the form of a violated inequality in polynomial time. And it's not trivial because there's an exponential number of inequalities. So we have to somehow find a violated one if one exists without checking them all one by one. So here's how we implement the separation oracle for this particular system. So again, the input to the separation oracle is Z star and ZIS for all bidder bundle pairs. Well, first thing we're going to do, we're just going to check that. It's only one constraint. Okay? If that's violated, we're done. So it's infeasible, and here's why. Okay? So for the rest of the proof, let's assume it passes that test. Let's assume the ZISs and Z star actually satisfy this. And let's move on to the exponentially many allocations. And let's actually use the promise that I said. We're going to use the existence of some good randomized rounding algorithm, which is not a scaling algorithm, to prove that there is one a good one, which is a scaling algorithm. So we haven't used the existence of last week's algorithm yet. So here's where that comes in. So step 2. So we have this allegedly feasible dual solution, these ZISs, these pseudo valuations. So what we're going to do now is we're going to interpret these ZISs, even though they're just these sort of made up numbers we were given to as a possibly dual feasible solution. We're going to think of them as valuations that we're going to feed into last week's algorithm. Now the ZISs could be positive or negative, and the negative ones are annoying. So let's actually just treat the negatives as 0. Okay. So otherwise, so let me write them as the Z plus ISs, which is just the max of 0 and ZIS. Interpret these as valuations. And I'm going to run last week's algorithm on these valuations. Okay? So this is inside our separation oracle. We're doing this. This is getting pretty meta. Okay? This is getting pretty, so we're actually, because you might remember, what was the first step of our old algorithm? Right? Solves an LP, right? Using the ellipsoid method, actually, right? But for now, just think of it as a black box that we have this algorithm from last week that gives us a 1 minus epsilon approximation. So use old algorithm. One thing that's important is the algorithm from last week, remember the valuations are general. Okay, we didn't assume they were submodular, we didn't even assume they were monotone, we assumed nothing. So, which is good, because we're feeding it in these ZISs, which we know nothing about. Okay? So we're just saying, hey, algorithm, think of these as valuations, come up with a near optimal allocation for these ZISs. Okay? And we invoke last week's algorithm as a black box. So use old algorithm to compute an allocation, S1 up to Sn, that's almost optimal. Actually, sorry, I misspoke. Slightly, I slightly misspoke. Let me correct how we use last week's algorithm. Okay, so remember, last week's algorithm, when I described it, it took as input this optimal LP solution, and then it did randomized rounding. But at the very opening of today's lecture, I said, actually, if you think about what randomized rounding did, it didn't care what LP solution you gave it. Whatever LP solution you gave it, it does randomized rounding, and we proved it gives you back an allocation which is almost as good as that LP solution. Okay? So what we're going to do is we're going to invoke the randomized rounding from last week, and we're going to give it this LP solution Y star that we started with. Okay? So what we're going to get is, right, to compute allocation with, so what was the guarantee from last week's algorithm? We're guaranteed that the pseudo welfare, so treating these Z pluses as valuations, is almost as good as the fractional value of Y star. Okay? So actually, we're doing something simpler than I said at first. Okay? So we're here in the separation oracle. Like I said, we first verify this final constraint. Assuming it passes this test, we say, okay, interpret these ZISs, zeroed out, as valuations. And now, just do randomized rounding using Y star. Okay? So Y star was this LP solution we were given at the very beginning. Okay? So we just the same old randomized rounding algorithm we did last week. What we proved is that randomized rounding gives you this guarantee. Okay? You get a feasible solution, you lose only 1 minus epsilon with respect to the LP solution you started with. Okay? Which is what we proved at the end of last week. All right, so now, what do we know about this quantity on the right-hand side? Well, this is, right, so remember Z plus was obtained from the Z's just by making negative numbers 0. So this is only smaller with respect to the Z's. And we check that the last constraint holds, right? That was the first step. So this is at least Z star. Okay? So this basically gives us a violated constraint. Okay? So remember, the first set of constraints says everything has to have pseudo-welfare at most Z star. What this shows is that basically by using the algorithm from last week, it computes an allocation for us corresponding to one of those constraints with pseudo-welfare strictly bigger than Z star. The one sort of hitch is that it's with respect to these Z pluses, but basically just if any of the ZISs are negative, you just delete that bundle and it's still a violated constraint. Okay? So again, the high level point here is that algorithm from last week is a separation oracle that in polynomial time will compute a violated constraint of this family. Okay? So yields violated constraint. Okay. All right. So let me just sort of explain where we are. We're basically done. So let me explain why we're done. So we wrote down this linear system, which was feasible if and only if there existed a scaling algorithm. We showed that feasibility of that linear system was characterized by infeasibility of the dual linear system. We just invoked the ellipsoid algorithm on the dual linear system. I showed you how to compute a violated constraint in polynomial time. And actually, if you think about it, notice, right, so separation oracles usually do one of two things. Either they say, yeah, you're feasible, or they say, no, you're not, and here's a violated constraint. And I just showed that no matter what Z star and ZIS is you give the separation oracle, it computes a violated constraint. Either the last constraint's violated, or if it's not, you use the algorithm from last week to exhibit a violated constraint of the first family. It never actually outputs feasible. Okay? So our separation oracle always successfully finds a violated constraint. Right? So that means it's an infeasible dual system. Right? There's always a violated constraint, no matter what you give it. Okay? So, upshot, first of all, D2 infeasible. Okay. Always found violation, which means that LP2 is feasible. So there is a scaling algorithm, a 1 minus epsilon scaling algorithm. And now there's this issue. So the last comment is just to address the discussion from earlier, which is okay. We can run the ellipsoid on the dual program. So how do we actually, how do we actually compute the scaling algorithm? So we run ellipsoid on this dual program to certify infeasibility. So what do I mean? Okay, so the ellipsoid algorithm is a polynomial time algorithm. If you run it for something like n to the 5th iterations, if an LP is feasible, it's guaranteed to find you a feasible solution. So what do? You run it on D2, you wait n to the 5th iterations, and all along it's been generated violating inequalities. Right? And at this point you've exceeded the running time bound that we know is true for the ellipsoid algorithm. Okay? So we know it's infeasible after the n to the 5th iterations, because if it was feasible it would have found one. We have proofs of that. So we know the dual system's infeasible, and moreover these n to the 5th inequalities that the ellipsoid algorithm has generated is sufficient to conclude infeasibility. For all ellipsoid knows, these are the only n to the 5th constraints in the world. There aren't any others. Okay? So we can imagine as if this dual linear system actually only had the n to the 5th constraints that the ellipsoid algorithm generated. Okay? If we delete all the rest, we only have these n to the 5th constraints generated, it's still infeasible. Okay? Now we do Ollie's suggestion, which is, well, oh, that's great. So in the dual linear system, we always only had a polynomial number of decision variables. Now we're saying ellipsoid algorithm has helped us focus on a polynomial-sized subset of constraints sufficient to certify infeasibility. So now if we take the dual back, using Farkas or strong duality again, we get a feasible linear system that has primal variables corresponding only to the n to the 5th constraints that we generated here. So we get a primal linear system with a polynomial number of variables. As always, it has only a polynomial number of constraints, so you can solve that primal linear system explicitly. Okay? And because it only has n to the 5th decision variables, you're going to get a result which has only n to the 5th support at most. Okay? So, generates polynomial number of constraints. And remember, constraints in the dual correspond to allocations. Where here L is just the maximum number of iterations that the ellipsoid algorithm might ever need to find a feasible solution. And so then what you do is you solve LP2, except only with the decision variables. Sorry, this should be omega 1 up to omega L. So those are the allocations over in the dual. And you solve the primal with only the decision variables corresponding to these L constraints. And the whole point is this is still feasible even though you've thrown out almost all of the decision variables because the dual is still infeasible. Okay? And this you can solve explicitly. You don't even have to use ellipsoid if you don't want. Polynomial number of variables, polynomial number of constraints. Okay? And so that finally completes the proof of Levi-Swamy. So this is how you compute using a second linear program, a scaling algorithm. That's just a list of probabilities. It says, oh, tell me your LP solution, tell me your Y star. Okay, well then output this allocation with 1% probability, this other one with 3% probability, and so on. By the linear programming constraints, it has the scaling guarantee. If the LP suggests you output something with 4% probability, you're going to do it with 4% times 1 minus epsilon. And that will be true for every single bidder I and every single bundle S. As a result, when you optimize over the linear program to compute Y star, you're actually, unbeknownst to you, optimizing over the distributional range. So that gives you the MIDR property, and that's what gives you the DSIC mechanism with a 1 minus epsilon guarantee. Okay, hardest lecture of the quarter over. I'll see you in 10 minutes.